Oh, yes, here it is. So now we're recording. So welcome to the analytics session of the course. One of you were asking where Curitiba is. I'm currently in Brazil, and this is why we are having an online session. So the 3 sessions of today and then the next 3 sessions after the holidays will deal with 2 particular things. The first thing is get you acquainted with some analytics methodology in order to drive experiments, data-driven experiments. And well, at the very beginning of the course, you had an installation session with by installing R and other tools that you are already using. The idea of my sessions is to show you alternatives of externalization that can provide different scales of execution, and that can eventually be interesting to give more independence to the execution of your experiments, and also to test a little bit of the cloud provision of services regarding data analytics. So that's the main message that I will be driving in my sessions. I'm not sure that you are. Are you? I'm not sure that you are seeing my slides moving. Is this true? I don't know why. All right. Can somebody tell me if you are looking to the to a different slide than the one that says that the session is beginning at some moment?
We are still in that one.
No, it's not moving.
Stop the sharing, and then I restart the sharing to make sure that you are watching what I'm watching too. Just give me 1 second. So let's see. I think that now you should. Right. Right. Okay. So today it will be like I will try to, by the very end of the morning, to start introducing you to the externalization tools that we will be using. So today is a little bit of theoretic content, but then the next session after the holidays will be completely practical. You will see that there are very cool and interesting tools to be used. And of course, we will be discussing the relationship that there is with the exercises that you have been performing in Mongo, and of course in R. Now, I introduce myself before we go on. I'm Genoveva Vargas-Solar. I'm principal scientist at CNRS. I work at the LIRIS lab in Lyon. And normally the course is, well, it has been on for quite a bit of time. I have a site where I maintain also the content of the course, but in our case, it will be Casein that will help us to share all the material, and then the YouTube videos that I will be recording during the sessions I will teach, so that you can have everything in the same invite. Just some administrative and disclaimer aspects. I will be using as much as possible inclusive language. So I will try to promote these principles in the content of the course and in the content of well, in my speech. I will also share the disclaimer of these aspects so that if you want to adhere to them, you can use them in the exercises that we will be performing. And then, so that's the first thing. And the second thing is that I will kindly ask you to turn off your mics. Feel free to open the cameras. I see that Eric has the camera on, so do not be shy, and if you can open the cameras. And at every moment, feel free to ask questions. You can open your mics or use the chat. So okay, so it seems that Sumant is not listening to the audio. Are the others listening to the audio?
Yes, personally, I'm Eric. I'm listening. Do you like us to activate the video or not? The
I mean,
cam,
it depends on you. It depends on you. I mean, you
Okay.
can come back and forth, and then, or you
Because
can, right.
sometimes sometimes
Yes,
it's
it's better to see the faces that,
Yeah.
but I mean, as you wish. There is no problem.
Okay. Okay.
So, Sumant, let me just tell, I have to write on the chat because it seems that Sumant is not having the audio. Audio. We'll see what happens. Okay, so with this, let's enter into the matter. And well, until now, there's been a lot of content, as I have seen in the slides of my colleagues, about big data. And some of the aspects that have been introduced, and on top of which I will insist a lot, is that, of course, in this course, we will try to go beyond the buzzword and try to figure out how the properties related to big data have an impact in data-driven analytics. Okay, so that's I would say that that's the most important thing that you must consider when we talk about big data, is properties, and then the impact in many different aspects, in the way you design your experiments, and in the way you have to deal with the data itself, and then how, which are the tools that you are going to use depending in the moment of the design of your experiment. Okay, so I believe that in the previous sessions, particularly when you have started discussing about Mongo and about other programming models like MapReduce, what is the property that has been related to the fact that we need parallel models in order to do data processing?
Consistency.
Yes, well, that's the properties, that's a non-functional properties of data management. But what about big data? So let's go to the properties. What are the main 5 properties that can be associated to big data? You can have a look at the
even
slides.
remember.
I will never know if you look at the slides.
Integrity. Yeah.
Those are the properties of data management. Remember, there are the V models. Volume. This is why big data is called big data, because the thing that drives the entrance to the movement, because it's a trendy movement in data management, is volume. Okay, so this is the point of the slides we are having a look to now. It's that in any case, volume has always computing science, in fact. Okay, so we could go to the moon with 64K, and now we are able to have artificial intelligence, processing of the brain, control of huge industry 4.0 settings, and this implies that we have to deal with a huge volume of data. And why is it important, or complicated? Why is it a buzzword, thinking about volume?
Because of time needed to compute it, to compute the calculations,
Right.
precisely, I suppose,
Mhm.
and space also needed to store and to maintain the data.
Exactly. And when we talk about the time needing to be processed, it is because normally we use greedy algorithms to process the data. If we didn't use this kind of algorithms, then it would be less important and have less impact to the fact that we are using big volumes of data. Okay, so greedy in computing science, what we mean is that it consumes algorithms and processing tasks, consume a lot of memory, main memory, and a lot of storage, and of course, a lot of computing cycles. Okay? So we move to, particularly in the previous sessions, you have seen that we move to parallel programming because we have the hope that with this kind of programming model, we can come through the fact that greedy algorithms take a lot of time to execute big volumes of data.
Mm.
So that's the issue about volume, okay? And of course, there is the storage support, you are right. We have to figure out strategies to deal with these volumes of data, to make them accessible when we need, and also to let them persist. And also, there is the notion of durability. When I have a lot of data, I have invested in having this data. And so this investment, I want it to last as long as possible, okay? So I need to have strategies in order to allow this data be maintained along long periods of time. And this is the issue about the first V, which is volume. What is another V that you have addressed?
Oh.
Variety,
Velocity.
velocity, exactly. So let's talk about velocity. What is the issue about velocity? What is velocity?
Not
Tell
sure we
her.
talked
Don't
about
leave
this.
her alone.
What is velocity? Normally speed velocity.
Velocity, of course. Well, it is important that we associate the term velocity with speed, but this is speed of production. The production rate of the data is a problem when we want to process it. Okay, and why?
Because of time response, no? Or
More than that, it's true, it's time response, but so imagine that there is a flow, no?
yes.
And comes and comes and comes and comes, and then we have a program that needs to process this flow.
You mean time stamping, maybe, or
Well, that's the solution. The problem is that we are dealing, our machines are discrete machines. Well, you are in another engineering discipline, but maybe when you started programming, you were taught about discretization of, discrete mathematics in order to program. If you haven't, the thing is that the computing of the normal computers that we use until now, there are new others in the market today, but the classic ones are discrete processing elements. Yet, when we talk about flows, we have continuous flows. And the challenge is to give the impression both to the processing and to the consumption of the data that we are processing and consuming flows, despite of the fact that in fact these flows are being discretized. So in fact, what happens is that we get a window, we process it, and then it is consumed, and then another window of data come, and this windowing process allows us to have the illusion that we are processing the data continuously, but in fact we're not. And this is why timestamping, for example, has its importance. Okay, because it is through timestamps that we are going to make sure that we process all the data in the right order and that we do not lose information. Okay, but because of course, since we are windowing and the data is coming continuously, we might, if we don't have the right windowing strategy, might lose data. Okay, so the challenge is how to figure out a solution that, despite the fact that the thing is continuous, we do not lose data and are able to process everything. Okay, and there, parallelism comes back to the scene. If I have different processing elements consuming, then the possibility of not losing information and processing all the information is possible. Yet the challenge, particularly with this type of data, is that if I'm fragmenting my flows, I have to make sure that I still have an order on the flows. Okay? So this is the big challenge of velocity. Remember, pace of production. And then, of course, volume comes in a traversal as a traversal property, because since flows of data are coming, then the volume starts to be large, despite the fact that we decide or not to store these flows. And then the other question is, am I going to store and keep track of all the flows that are coming? This is huge, right? Or am I going to have a storage strategy to keep what is important and then discard what is not important, or things that I can reconstitute by through an initial bunch that I have. Okay, and we all have engineering studies. We know that there are mathematical models that, given some initial seed of data, we can reproduce eventually other data that might have come, but we didn't decide that we didn't store. Okay, so that's the very issue of the thing.
Sorry, Genoa,
Yes.
are you showing different slides now? Because I only
I'm discussing on, because well, I thought that the V's were in your mind, so I was starting to go to the highway and then
because I don't know the V's.
yeah, but then I stopped my car and I said, well, let's have a look at the properties and then we continue on the highway. Okay, so well, we have to. What is the next one? We have 5 at least.
5 V's. Okay, I don't know even one.
Okay, so volume, velocity, variety.
Variety.
Variety means that we have heterogeneity. Consider, for example, in an Industry 4.0 setting, you have the sensors associated to the machines. You have sensors observing the production flow of, for example, a workshop, right? So you are also collecting data about the status of the arrival of raw elements that will help you run the process. There are other data analyzing the amount of production that you're having with respect to the orders you have to honor. And all these data are in fact very heterogeneous, both in their structure, in their content, but also on the, for example, on the production phase. pace, sorry. So it's not the same of having sensors that are producing data with a high degree of variety than other data, for example, the orders. The orders move in a slower pace. Okay, so this heterogeneity has to be addressed. And the problem is that in between we have volume. And if we have a lot of volume, addressing heterogeneity, it's costly. Okay. Normally in computing science, what we have been doing, and particularly in data management, is if you have heterogeneous data, what we have is a pivot representation, more or less as we do in mathematics. So we have a pivot representation that homogenizes all the data, and then we work with them. But if you are talking about a lot of volume, then this costs a lot of time also. Okay, so the idea is to stop doing this and try to address heterogeneity, so variety, with as less as preparation possible. Okay, so that's variety. So we have three. Then
I can think of value.
Value is a very important property, because until the trend of big data, people have never thought to estimate the cost of having the whole data cycle of a data collection. The cost, for example, of collecting your data, economic cost I'm talking about. The cost of processing big volumes of data. The cost of processing data with a high velocity pace. Okay, and now that volume is in the arena, beyond the fact that we want to have good responses and reduce the use or optimize the use of computing resources as possible, we have to think about how much does it cost to maintain and process our data. Of course, if you imagine that you have many servers, many storage disks, these will cost, have a cost in an organization. And then if I'm telling you that you need to maintain this a long time, this means that you have to also invest. Sorry, someone is coming and I don't know where the person is. Let's see. So all this investment impacts the economic cost of the maintenance of the data, also of the processing of the data. And this has to be considered particularly, for example, in data-driven experiments. Okay, we are in smart analytics. We are going to use the data to make decisions. For example, when are we going to maintain a set of machines, for example, in a workshop, or the possibility of a machine to break down and then harm our production. So all these questions that are answered using data have a cost, an economic cost, and this is related to the value of the data. Every day, for example, you are stream music consumers, we have this kind of thing. The value, for example, I don't know, in settings like iTunes, is you can have a cost per song. The song is data, and so they provide a cost, a price to access this. In other streaming settings, you subscribe, and depending on your subscription, you will have different conditions for accessing your data, with publicity, with not publicity, online, or even if you are disconnected. These are economic models that have been associated to data because of the fact that now value is an important property of the data. So that is this clear?
So by value, you meant
Economic, how much does
money
it,
value.
money. Yes, money. Then, of course, there are other value models, but essentially, this is all about money. How much does it cost to maintain my data and process my data? And how much does it cost for me to have decision-making processes based on data analytics? Okay, so this is the question, and this is why value has to be considered when we are dealing with this data. And last but not least, so remember, we said volume, velocity, variety, value, and veracity. Veracity is very important. How do we make sure that our data is true, represents a real observation of some complex system that we are observing? Okay, for example, if we think on Industry 4.0 or in different settings in the same perspective, we are observing complex systems, and data are being collected and represent the status of this total or partial of the complex system. And how do we make sure that these data do not have errors, that such that when we use it in order to analyze it and then eventually make decisions, that we do not make the wrong decisions because our input data has a low degree of veracity? Yet veracity, for example, you have some sessions with the relational model, right? And Professor Bobino introduced you to fragmentation, vertical fragmentation, etc. In this context, and particularly when you use relational solutions, in fact, are interesting because the reasoning is mathematical. Okay, so the relations are relations in the mathematical sense. They have mathematical properties, and all the game that we have to play when we deal with this type of data is that we maintain certain mathematical properties across the different processes that we perform on top of the data. If we update them, if we use them to answer a query, etc. These are guarantees that have a huge level of veracity, okay? Yet when we start moving, for example, you are playing with Mongo, I believe, now, certain elements of veracity are relaxed in the exercise that you have or you are performing. You've seen that the collection, for example, has not all the attributes are with real data. Okay, some of them are null values. So this means that the veracity of the collection is not very high. But this is not a problem. I mean, this says only that we have to, first of all, evaluate the degree of veracity of initial data when we are processing it. And then when we produce for example, clean models, the degree of veracity that we achieve by cleaning or by processing the data in order to be used to, for example, for making decisions or for answering factual questions. Okay, so that's the key challenge of veracity. Okay, but anyway, we have to accept that by construction, data may have low levels of veracity that we have to face and to solve across the different processing tasks that we can perform on top of them. So this is a very important set of properties that you have to bear in mind. And this will show that you went to the university and that you are going beyond the buzzword big data and that you know beyond the buzzword, which are the different properties that have really be taken into consideration in order to have the expectation to perform smart analytics of the data and eventually make decisions and solve your discipline problems. Right, so just for the record, regarding volume, there is a new trend trying to consider that in any case, in normal conditions, we are going to deal with a lot of data, okay? And that we need new units in order to measure the volume of our data. And these new measures say the following. For example, during many years, particularly, I mean, big data has like 15 years of existence, more or less. Okay, so it's not longer a real buzz element. But anyway, people started to think that yottabytes, this much of data, was like a huge target to consider. Right? Then we saw that with social networks, with the evolution of technology, we very fast achieved these sizes. And then for new sizes, the idea is to consider, for example, that the minimum unit of real big data processing will be thousands of yottabytes. Okay, and this will be called a brontobyte. So we are going to talk about how many brontobytes do you have in your local disk sitting in your living room, for example, right? So today, I would say that in many of our devices and many of the disks that we have access to in Lambda users use is on the order of terabytes. You have smartphones with this space, no? Or if you are users of Google Drive or OneDrive or this, they provide you with at least a tera or 2 teras of storage. Okay, so this is a normal thing. So very easy. We can, if we are an organization or we are studying complex systems that produce a lot of data, we can easily go beyond this. Okay, and this is why people have started to think about this. And if you are interested in having a look at this, the trend and the initiative has been discussed in IEEE. And so the idea is to say that big data, dealing with big data will be the day-by-day situation of any person using data. And so they discuss, of course, about volume, but also the killer applications, right? That are using this kind of volumes. And one of the killer applications that was identified in those years was the study of the brain, right? So together with this, the other discussion is having new architectures, new computing architectures, so that it will be more or less natural to deal with these kinds of data. Okay, so we have seen this, and you have discussed this with Professor Bobino, and now what we are going to do here is the 6 sessions that we are going to work together will concern 2 elements. So once we have data with these different properties, we want to use them and exploit them, okay? And so first of all, there are different new sciences that have emerged that provide and have developed methodologies in order to exploit these kinds of data. Some of them are more users than than providers of the methodologies like social data sciences or digital humanities, but others are really proposing real new methodologies in order to exploit data with these different properties. One is network science. Network science is all about graphs, okay? So the research question of network science is, well, the hypothesis more than the research question is, any complex system can be represented as a network. And if we manage to use the right network representation for a complex system, then we can apply operations on the network and do understanding, so model the phenomena and also do prediction, okay? And the way we transform network representation in the computer is through graphs. So graph theory, the one that we learn in mathematics, is completely applied and exploited in order to process and analyze the data, with the idea that the conclusions that we can drive out of the study of these graphs is very accurate and representative of very complex phenomena. Okay? For example, pandemics has been a complex phenomenon to study, and with the use of this network science methodology, it has been possible to understand, for example, the way pandemics was spread around the world and different critical strategies to apply in order to deal with it. Okay, so that's one of the new sciences that are useful to apply when we deal with these properties of data. And the other is computational science. So in a minute, we will see that once we move to more analytical questions and not factual questions, particularly in the era of artificial intelligence, many data scientists address very fast the problems with artificial intelligence. Just the position of computational sciences is that we already in engineering use numerical models that provide very clear and very controlled analytics on the data. Okay, and besides, they are less costly as other new trend solutions. So the idea is to have problems, particularly related to complex phenomena, try to model them mathematically, and then if the mathematical model is too difficult to be expressed, then move to alternative solutions. Okay, and that's so people normally the idea is to use a lot of statistics, a lot of probability, and the numerical methods that we all learn in our engineering studies in order to have a first strategy to address the problems, data-driven problems, and then eventually, if this is not possible, to move to other alternatives. But in any case, there are two elements that have to be considered. This one you have already discussed in the previous sessions, is that we need new algorithms, okay, new mathematical models in order to address many of the problems that are based on data, okay? So that's the first thing. So choosing the right mathematical model in order to address a problem is something that we have to learn. And the second thing is that when we work with data-driven experiments and problem-solving strategies, in fact, what we are doing is experimentation, okay? But the experimentation is not done in a lab, but it's done on computing support. And so the question is, which is the right architecture that we need in order to perform our experiments? Okay, and how much CPU cycles do I need? And are these CPU cycles fast enough in order that I can solve my problems in reasonable time? And how much of main memory will I need in order to address my problems? Okay, so that's the laboratory understanding, which is the laboratory that we have to design in order to perform our experiments. Okay. Now, some of the problems are addressed by IT groups. Okay, if you will be working probably in industry or in if you decide to continue your studies on PhD, anyway, you will address this decision-making aspect, which are the needs for my experiment. And then, of course, an IT group can help you with the technical matters, but you have to be able to state the requirements, and therefore you need to be acquainted and aware of the architectural elements that you need in order to set your experiment. And so we'll be moving from this to this in the sessions we are going to work together. Now, just to make sure that that you haven't forgotten the definition of big data, I saw that you have a look at in the previous sessions, but I'm going to insist. So when we talk about big data, we talk about data collection, and their characteristics is that they are difficult to process in single machines and traditional databases. Okay, so everything that we can process in traditional solutions is not a problem, in fact. Okay, it's just a technical problem, but there are no challenges to be addressed. Okay, and then once our tools start to be limited, then and we need new generation of tools, methods, and technologies in order to collect, process, and analyze the data, then we are talking about big data. Okay. And so that's something that Professor Bobino, I think that introduced already. So this is why we need parallel processing and distributed storage, okay? And this is the main purpose of having discussed horizontal and vertical fragmentation. Tell me if you are not sure whether you really address these aspects in the previous sessions, okay? So that I do not say that you have already seen this, and in fact you have. Okay, but I believe that you studied vertical and horizontal fragmentation. And so this is because we need strategies in order to distribute the storage, okay? And the good strategies for that. And then we have already said, why do we need parallel processing? Now, just to have a motivation example of what a complete setting of data-driven management in, for example, in industry that can use parallel processing, for example, Hadoop, but any other parallel processing, is the following. You can see that here in the bottom of the figure, we have computer numerical control machines. So this means that we can monitor the conditions of the internal conditions of the machines and also of the workload that they are addressing. Then they are producing data, and these data are stored in databases or in archives, the way you want. And then eventually they can be processed on parallel settings. I just remind you, this is something that you should have discussed previously, but there are two elements when we talk about MapReduce and Hadoop solutions is that there is the storage aspect and there is the processing aspect. When we talk about storage, the main question is whether we are using file systems or whether we are using cluster-based data storage solutions. When you studied this perspective, you were introduced to, for example, distributed file systems, HDFS. For example, I think that, well, I saw in the slides that were shared in Casein that you had a discussion on the way a distributed file system works, okay? So this is, the idea is that you have plenty of disks that provide you with storage support. And in order to have a global and optimized way of accessing these disks, then you have a distributed file system that gives you the illusion that you see only one disk, but in fact you have farms of disks where the data is distributed and replicated. Okay, and when you address to the file system, you will ask for, as we all do when we ask the file system, when we choose our files in the file system or from a program, you ask for the data, and then the file system connects you to the right space of the disk so that you can retrieve your data. Okay, so that's storage, and then you saw that if you need more than that, then you can have cluster-based solutions like Mongo, okay? And then once you have this, then you are ready to process the data, playing with matrices, doing extrapolation, running Gauss-Jordan numerical model in order to perform some analysis, okay? These kind of things are done in the parallel processing element of a solution. And so once you have this hardware or very close to hardware tools, then here you can find all the software support that will help you, you or the IT system with the one you work with, perform your analytics. And then the results will be also maintained here and here. And then people can have a nice view of the solutions in visualizations, in aggregated perspectives, so that these people can make decisions on, for example, industrial processes or any other process that is addressed with in this kind of setting. And so you've been here and more or less here, okay? And now we are really going to have an extensive interaction on the red layer, okay? Now, at the very end of Christophe's session, he gave the list of things that you cannot do with solutions like Mongo or relational databases, etc. But I want to point out the things that you can do until you have like classic storage and query solutions as the one you have been using until now, right? So you can, for example, answer questions to decide how to distribute data across different data management systems. So with Mongo, you know that Mongo is a cluster-based solution. So you have the tool and the different interfaces that allow you to make decisions or leave the decision making to the process to the system, so that it can decide which is the best way to distribute data across these different either management systems or disks. And there you can think about availability, about concurrent access, and about consistency. Okay, so When we fragment, we have, particularly when we duplicate the data, this allows to have a lot of availability. But if we modify the data, we create different copies. And at some point, they have to be consolidated so that all the users of the data can have the same perspective of the data that they are using, okay? So that's something that can be answered using classic solutions. And then, well, the decision-making problem is in general manual, so you need the IT support for doing this. And then another thing that can be done with classic solutions is, of course, query. We all query data when we use Google search engines, when we use, well, now you are playing with the practice of Mongo, so you are also playing with queries. And querying is all about locating the right data across different disks and eventually ensure that this lookup of the data is done in an optimized manner. Okay, particularly if we are talking of a lot of fragmented and replicated data, and where volume and velocity are there as driving and teasing properties to be taken into consideration in the strategies that are provided by systems for solving querying aspects. Have you already finished the exercise on Mongo?
Supposed to, but not yet.
Not yet. At some point in the exercise, there are questions regarding indexation, indexing the data, and having a look at the execution plan. And well, these questions are in fact related to this. We want to make sure that our queries are rely when they are executed on the right organization of the data, such that they can go faster than if they were not. Okay, so this is an important thing to do, and this is also related to the fact that if we have good index data, then somehow we are contributing to good optimizations of the queries. This is the message to be kept in mind beyond answering the exercise that you have to do. Okay, so now we are moving to a little bit of more scale. So we will be talking and trying to talk about huge volumes of data, and the idea that the whole idea and the whole purpose of the analytics we are going to discuss is that we want to answer questions that are not factual questions and that increase somehow the return of investment of this process. Okay, we want to do better in a company, we want to do better in a production line, we want to do better in climate observation. Any answer that we will provide with analytics has to improve the conditions in which we answer difficult questions. Okay, if we do not improve, then it's pointless to do analytics. Okay, so that's very important. And then if we are in industry, this of course has to be seen in, for example, improving the production, improving the gains that you have in a company, etc. This is the reason why you should invest human resources and also economic resources in order to deal with data. Otherwise, don't do that. And particularly because in real conditions, there should be investment in buying or accessing somehow computing resources, okay? And this can be costly. Now, as I said at the very end of the previous sessions with Professor Bobino, he said, okay, so the questions that cannot be answered with NoSQL stores or classic solutions are of two types. First of all, classification. Okay, so examples of questions regarding classification is giving a set of images, for example, of steel sheets, identify those that have wounds in the central area. And this was one of our projects with in metallurgic in a metallurgic project that we had. They had this problem, right? So there were the steel sheets going through a line, through a production line, and some of them were bonded through by the line, I mean by the elements of the line, and they wanted to identify them in order to separate them and just classify the good ones and have the wounded ones separated from the batches of steel sheets. So that's a classification problem. Okay, then which are the characteristics of the clients willing to buy electric vehicles, so that we can target our market and sell a lot of our electric vehicles, for example. Which anomalies cause fatal breakdown in machines? Again, we used to have a project with China, and this was the thing. They had a workshop line, and with different machines that, I mean, the products went through sequentially from one machine to another. And there were, of course, orders to be honored. And the thing was that if a machine broke down, a robot has to take the products from this machine and then put them in a machine of the same type, such that the production line was not completely harmed, right? So since the machines can be observed, the idea was to identify anomalies in the machine and then determine whether an anomaly potentially could generate a fatal break. Okay, and this helped to also to place the machines in the workshop, and then the decision that was made to let the robots go from one machine to another. Okay, so those are classification problems. And then the second type of queries that cannot be answered with factual data are, for example, are prediction queries, right? So the expected evolution of the market of electric vehicles, okay? Or the expected active life of a manufacturing machine before its first breakdown. So I think that Christophe presented you the problem is that if you predict with quite a good precision whether a machine is going to fail or in some period of time, then you can decide, for example, for maintenance in preventive manners and avoid fatal break of machines that can harm your production line, for example. Okay, so how do we address these questions? The answer is that this calls for experiment. So they cannot be answered in one shot, as we are used in, for example, Mongo or the like, but now we have to step by step address the question, process the data, and then come close to the answers, okay? And this strategy of processing the data, we will call it an experiment. And the very challenge is to design such an experiment. Okay, first, and then assess the results of the different phases to expect having a close answer to the questions. And that's also the very difference with respect to factual queries, is that in a factual query, you have a precise and definite answer. The average of the salary of employees of department A. There is no question. If I have the complete data of the salaries of my employees, then the average value will be there. Okay, it's definite. Whereas here, all the results are close to an answer, but they are never definite, and they always have an error margin. Okay, so that's the main difference between the questions that can be answered factually and these new types of questions. Now, today, these type of questions are methodologically answered, and the answer is designed, using the methodologies proposed by a science called data science. Okay. So what the sessions that working on are data science sessions. Okay, we're going to learn data science. So the principle of data science is that the representation of complex environments by rich data opens a possibility of applying scientific knowledge regarding how to infer facts or observations from data. Okay, now we are not deducing, we are inferring. Okay, that's the main element of the science. And then, of course, any science has its own methodologies. Okay, so data science provides a methodology by which actionable insights can be inferred from data. Okay, the principle, the very hypothesis on the basis of data science is that we will have enough observations of an object of study represented through data, and we are going to apply some methodologies and have insight or foresights on about the problem given data. And then there are other aspects that are surround this very initial hypothesis. There are elements like ethical elements. There's methodology, of course. There are business models. For example, if we want to associate value to the solutions, we have to estimate the economic value, and so we need business models in order to estimate the cost and then the price of our solutions. Then, of course, how to deal with the data. We need data engineering, we need data governance, and all these elements will calibrate the way we design our experiments. And the very objective is produce beliefs informed by data. So no decision-making will be made without evidence on data, okay? And without the possibility of explaining which was the process that drove to some decision. Okay, that's the real objective of data science. And because in the absence of data, in fact, beliefs are uninformed and decisions are based on best practices and intuition. And the problem with best practices is not that they are there, is that best practices normally are acquired and are immaterial value in your assets, in your human assets, right? So if they are not methodologically materialized, then if the person leaves your organization, etc., then this knowledge is lost, and this is not good. Okay, so the first drive that we have to bear in mind is this slogan that appeared very early in the big data, when big data started to be a buzzword, is that the data is everything and everything is data. The implication of this is that we assume that there is a possibility of having a digitalized representation of the object we are studying. Okay, so we need to use different technologies in order to produce enough data collect enough data such that that we can have a digitalized model of the object that we are studying. And this is why big data came into the arena. But the second, and here this is a kind of element of vocabulary to bear in mind, is that the underlying objective of data science and principally the thing that makes it possible to exist is that there is a phenomenon of datification. So this data is everything and everything is data is called datification. Okay, and so since we are digitalizing anything that we can, then we open the possibility to have analytical knowledge on the data. And this is done thanks to algorithms. So we constantly hear about algorithms. Algorithms, in fact, it's the general word to include, as I said, the numerical models that we learn in engineering from the very beginning of our education, and then also the other algorithms that are emerging now, for example, through the artificial intelligence trend, right? But anyway, so this analytical knowledge is produced by these elements that are called algorithms, right? And then, as I said, we want to make evidence-based decisions. And then the other characteristic that is important is that this goes for people and organizations, okay? For the first time, it's not only a problem of companies, but this datification touches all the humans in the world, okay? And so this is the element that changes the scale of what we want to do. So back to the, sorry, this is a nice animation, but it's not working well. The backbone are data. And so the idea is that we are going, the methodologies that have been developed in order to perform data science given datification is that we are going to weave data management. So the first part, the previous sessions that you have had with Professor Bobino had to do with data management, in fact, okay? Then greedy algorithms that we are going to have a look at, and then eventually you will have huge batches of regression techniques, etc., with Professor Jolie. So all these are greedy algorithms. And then also the programming models. You will see that in the historical moment in which we are, programming model, I mean, parallel computing is there, but it's hidden behind interfaces that allow us to think in general manners, and then the system makes sure that this is parallelized, okay? But anyway, parallel programming models are there, and they are not the only ones. That's important to know. And then all this, how is it deployed in different target architectures? Okay, for the time being, well, you have seen, for example, the preparation of RStudio on your machines. This means that the target architecture is the architecture provided by your machine or the machine in the school, no? Then with Mongo, you have started to see that another possibility of target architecture is having a cluster, right? So having a cluster of machines where you deploy Mongo and you can perform your queries is a new way, a new possibility of having more resources and then processing data. And we will see with me other ones. So it's not coffee break yet because what time is it? We have still like 15 minutes, and with this, well, I'm going to stop here to also to let you answer ask questions if you have, but also to tell you that the class, I mean the 3 sessions, will end at 12. So this means that I will give very short coffee breaks, the time to grab a coffee and then come back, such that the huge coffee break will be in fact going to have lunch at 12 instead of 12:30. Okay. So not coffee break now, but time to questions. Do you have questions or reactions or comments? So what have we learned until now? We remind the 5 properties. We understood their impact on the processing aspect. We've seen which are the queries that are factual queries and which are the ones that cannot be answered through classic solutions. And then we have introduced the notion of datification and the definition of data science. This is what we have done until now. And then the rest is to show you the interest with respect to your discipline, etc. Is that a good summary of what we have done these first minutes?
Yeah. Could we get back a little bit on queries that are factual ones? And the other one, because I'm not sure I quite well
Got the
understood.
message? Well,
Yes.
my comparison is maybe not glorious, because in this slide, what I pointed out was the problems that are addressed by classic solutions regarding queries, okay? But let's think about queries. When we use solutions like the relational model or like Mongo,
Yes.
fact, the principle is, first of all, that the data that we have in the database is complete, in the sense that everything that we have to know or that we know is stored in the database. Then other knowledge can come, but this time t, this is the truth, okay?
Mm.
And now the queries that you are going to ask on top of it are factual queries. So you do not want to discover anything beyond what you have in the database.
Mm-hmm.
And you cannot, in fact, right?
Yes.
How many restaurants are there? Which are the restaurants located in some area of the city? The average of the price of a 3-star restaurant in Grenoble, for example. You see, so they are factual queries. And this is this is done in an environment with specific properties. The first property is consistency. Okay, well, I'm talking about queries, but then you can update the data, right? And the thing that consistency says is that even if data is being modified, your queries and the answer of your queries will not be harmed. Okay, if I ask how many employees are there in subsequent moments on top of the same database, I will always have the same answer. I see that someone else has a question. I'm answering Eric, and then I go through your question. Okay, so
Thank you.
This is always stable because the database is stable, right?
Yes.
This also guarantees that despite the fact that many are querying the data, their concurrent access doesn't harm the vision that everyone has with respect to the data. This is true, for example, in the relational model, but this is not true in Mongo. This is why you have to copy the database and work with your own database. You did this, right? So there was the data collection in the exercise of Mongo, and then you have to copy this in your Mongo, create, well, not in your Mongo, but create a new data set on top of which you perform the queries. And this is because concurrent access is less hard than in relational solutions. But anyway, it is there, okay?
Mm-hmm.
Then fragmentation. I don't know if you discussed about sharding, but
A bit.
a bit. So the idea is that you have a data collection and you have many servers. The idea is that you are going to distribute your data more or less in a balanced manner throughout the different servers, such that when a query arrives, the system will drive your query to the right piece of data concern, right?
Mm-hmm.
And this is guaranteed by the querying execution system. And well, and then there's indexing and optimization behind. So the guarantee is that your queries will be executed in reasonable time. That's with regards to factual queries, okay? Done in a very precise and you know the conditions in which your queries are executed and which guarantees you have with respect to this execution.
Okay.
You saw the triangle, for example. So you know that in the case of Mongo that even if there is a connection fault of your cluster, you will eventually see consistent elements. These are guarantees, okay?
Mm.
Whereas we will see that in the experimental arena, there are no guarantees. At least not these ones.
Okay.
Mm-hmm. Now I have a raised hand. Do you want to
Yes,
open your mic? Okay.
Yeah. Professor, you mentioned about the having enough related data to apply some methods to get results is the fundamental assumption for data science.
Yes.
How we can be sure about the veracity of the right now the data that is actually is stored in the databases. What is this fundamental data veracity?
Well, first of all, you don't have a guarantee. You don't know. Part of your experiment must be to determine the veracity of the observations you are going to use. So the guarantee of veracity that you have in other settings is lost. You have to verify. And this you have already seen in the Mongo exercise, because in the Mongo exercise, there is dirty data. Many of the restaurants that are listed in the data collection have either empty attributes or have completely null values. And this is part of a low level of veracity. But since your queries are factual, well, more or less, because if you, for example, think about the average price of the restaurants of the list, your average result will be not very reliable because you have null values.
Right.
You see, so once we start moving out of mathematical representations of the data, the veracity of the data is no longer guaranteed. And this just means that we have to perform operations to determine to which extent we have this problem and then perform solutions in order to get rid of the problem.
Thank you.
Mm-hmm. More questions? So what I'm going to do is let's have like 10 minutes short break, and then we come back to continue with to start to zoom in into these experimental approaches. So 5 minutes to go. I'm going to stop recording. So when we come back, do not. So now the recording is in progress now. So before I move on, an important thing that I forgot to insist on is with regard to data science methodologies, is that, well, I said that the data collections are the backbone of the experiments, that we drive hypotheses that we have to state and we have to verify and contradict with our experiments. And this leads to valid conclusions. So in fact, I said the extent to which the results are answers to questions means that the results are close to the answer, but are never the answers. And this is because there are margins of errors associated with them. And the conclusions normally, instead of data, they are models, simulations, or eventually understanding of some problem. Okay, so also an important difference with respect to from factual queries with respect to experiments is that the result of an experiment is not data. The result of an experiment is some conclusion, which means a model or a simulation, or a conclusion in the form of a quantitative conclusion that is then interpreted by someone, by a human. Okay. Now, so let's get into the experiments. Well, when we talk about experiments in data science, we are talking about scientific experiments. Just to remind you, the general definition of what is a scientific experiment is any process in which measurements and tests are used within a typically controlled environment to support or refute a hypothesis. So a very, very important thing to remember and never forget is that if we do not state the hypothesis, we can apply the next generation of wonderful algorithms or whatever on top of a data collection. They do not mean anything. The experiment must be driven by a stated hypothesis, okay? And the objective is to evaluate the efficacy or likelihood of something previously untried, okay? So an experiment responds to something that has never been tried before, okay? We do not have a clue on the way we address the problem. And one of the answers to the hypothesis that is related to a problem is the experiment itself. Okay. Now, hypothesis, that's something that we know, but it's the point to remind is are supported propositions usually based on insights or prior research from which an investigation can be developed. Okay, so the novelty of the experiment doesn't mean that it does not rely in some observations. Okay, I suddenly start seeing people with a pattern of high temperature and problems to breathe, and many. So this is an observation, and then I can drive a hypothesis. Is a way of having flu and verify it or not, for example. Or I start seeing a pattern, for example, in the in the shields that I was talking about in metallurgic, I start having a look at a pattern where many shields are bonded in the same place. Okay, so the problem is to understand and to figure out why are these sheets of metal bonded in the same place. Okay, so that's an observation, and then we have the strategy to identify. Now, experiments are generally designed to identify causal relationship between variables. Okay, so normally what we will have in a data collection is observations represented as set of variables. Okay? And then out of this set of variables, we will proceed to reason about them in order to address our hypothesis. Now, without a good experiment design, no causal can be inferred from results. Okay, so the key here is the expression of the question. Okay, in the other factual queries, the key is having a good answer. Okay, and here is given a hypothesis is stating through the design of an experiment the question that will then provide elements to verify the hypothesis or contradict it. And the fuel of this complex process is data, which is the evidence we have. Now, this is in general, and then when we move to concretely to data science, there are 4 elements to consider regarding experiments. What is the best way to support or disprove the hypothesis? Okay. So you can design a data-driven experiment intended to disprove a hypothesis. Okay, for example, in this story of flu, I can perform an experiment willing to disapprove the fact that the symptoms observed in many people correspond to flu and not to a new disease. Right? This is the problem that we have during pandemics. What are we measuring and how? Okay, that's another very important thing that regards the question that was asked by your colleague before the coffee break. This is about data veracity. And a very important thing to consider is the conditions in which data are collected are very important. Okay, and the decision of the variables that we are we decide to observe with respect to a phenomenon. Right? And this decision is key to make it possible to verify our hypothesis. Then, what data do we need is, I might have a set of observations, but the question is, using this set of observations, which are stored in a data collection, can I really verify or disapprove my hypothesis? Are they enough? Can I answer my question just using this data collection? Okay. And then the tools. No, once I have this, then what are the tools that I'm going to use? And this is part of my experiment design. And all these questions must be at least addressed. In fact, we are talking about a loop, okay? But these questions have to be considered recurrently before the design of your experiment and then during the different design phases of the experiment. Now, this is the recipe, okay? Of course, you will see that from the recipe to the material, this design of the experiment. There is a trend to go through, but anyway, in fact, what we are going to do is creating a work. Okay, we are going to identify the set of steps that we think that would lead us to answer our question, which is validating or disapproving a hypothesis. Then this involves, as I said, formulating the hypothesis or a research question, because this, as I said, guides the whole process, okay? So never forget to state such a thing explicitly. Now, then determining the best way to gather data. Okay. You have the data, it's in raw conditions, and so you have to understand what is inside in order to see whether you can answer your question using this. Another possibility of setting is that you have the question, and then you are going to collect the data that will help you answer the question. Okay, so these are the two possibilities of driving a design. Then identifying problems and that's more mechanical things, sources of error that might that might harm your experiment, and then of course, if required, collecting the data. Now, an important thing, since we are saying that the question or the hypothesis drives the design of the experiment, well, it is important to understand which are the families of questions or objectives that we are going to state in order to perform experiments. In fact, they are like in an increasing spectrum of difficulty, if you want to see it like that, of complexity. And so you have, you have the types of questions here, and then you have here the possible tools that can be used in order to answer them, and here are the objectives. Okay, so at first, the most simple thing that we can be willing to achieve is ask questions of the type, what happened? Okay. When we ask questions of type, what happened, is we are in fact seeking for insights, and normally these questions can be answered using very classic techniques like descriptive analytics, okay? By performing statistics, we can have good insight of the situation that happened, okay? Then we can have questions like, why did it happen? Okay, so this is diagnostic analytics, and well, here we have many analytics techniques that are often used based on statistics or on probabilities in order to answer this. An important thing to consider with respect to the tool that we can use, in fact, I would say that the most precise way to address these questions, that these difficult types of questions, is by using mathematics. Okay. The issue with mathematical models is that they are very restrictive with respect to the mathematical properties that must respect the input data. And when we consider that the data are collected in very wild environments with sensors that can be working correctly or not, many different sensors of different types, data that can come from different sources, etc. So this variety of the data and this low degree of veracity makes it sometimes difficult to achieve the right mathematical properties that the mathematical models need in order to perform analytics. Okay. Example is regression. For example, when we apply regression, you need the data must have specific normalization patterns, okay, properties. And so sometimes it is possible to normalize the data, but other times not. And so if this is not possible, then other alternatives coming from other domains, for example, artificial intelligence, are not very strict on this kind of properties related to input data. And this is why sometimes it is interesting to apply. Okay. So when we are answering why did it happen type questions, we are seeking for insights. We want to understand. Okay. And then we can, once we understand a phenomenon, we can start asking questions like what will happen? Okay, can I predict? Can I have enough information to predict whether a machine will fail in the next month? Okay, or whether the price of a raw material that I use in my production line will increase its price. Okay. So when we are asking this, we are touching foresight. Here we still have mathematical models, for example, regression that can be used in order to predict situations. But here, very often we have also artificial intelligence. Machine learning is part of artificial intelligence, right? Machine learning or other types of artificial intelligence algorithms that work well with prediction analytics. And the summum is how can it make it happen, okay? This is why this is a kind of spectrum, because the idea is to acquire step by step and by performing experiments and understanding a phenomenon, etc. Try to have enough knowledge of this phenomenon such that eventually we can reproduce the phenomenon. We have enough data to know how to reproduce it and then how to face it. If there is how to face questions, okay? Answer questions. And this we are really seeking for optimization objectives. And very often, even if again, there are other mathematical models, but here is the arena of the artificial intelligence solutions. So questions until here? All is good? Okay. If there are no questions, let's continue. So how does this experiment workflow looks like? Well, in data science, an experiment workflow is called a data science pipeline. Okay. First, here in the bottom of the slide, you have the specific characteristics, both of the data and of the objectives of such an experiment. First of all, it is important to consider that data represent observations of an object of study. It can be a phenomenon, it can be pandemics, it can be the production line in a company, it can be the state of the evolution of the market of some product. These are observations, and normally they are represented as a set of variables, okay, that represent the observation. And these variables can be called features or attributes. Features is the vocabulary of analytics, and attributes is the vocabulary of databases, right? But anyway, you have records of observations with the readings, the values of the different variables that represent an observation. Every record is an observation. Okay, and that composes a data collection. Now, the objective of a query is analytics. So we can be looking for the different aspects that I have introduced here: hindsight, insight, and foresight. Okay, so this is the objective of the query, and they are expressed as workflows, as pipelines of operations that are guided essentially to the conditions and characteristics of the data. So again, your colleague some previous minutes asked, okay, so if the data is like has low degree, or I have to think on the veracity of the data, how do I do that? Because your steps in the experiment the first steps must be intended to verify this, okay? And then the result is a model or a prediction with very important associated assessment indexes or scores. Okay, you assess the result with respect to, I mean, the general answer is how precise is my result such that I can validate or not my hypothesis. Okay. Non-precise results cannot contribute in the validation or disapproval of a hypothesis. Then they are not definite because new observations can come. And that's, in fact, I have, every time that I study a phenomenon, I have a partial view of its behavior represented by a data collection, okay? And then if the phenomenon is continued to be observed, then I collect more data, and eventually, potentially, I can have a more complete observation of this phenomenon. Okay. And so this is why one of the reasons why the result is not definite. And in general, it is associated to a margin error, and several times also by comparison. In fact, we are going to design several versions of our experiment, and then varying the conditions in which the experiment is performed. And by comparison, I will seek for, I mean, every time I retry my experiment on different conditions, I'm seeking to obtain better precision scores and reduce my error margin, such that at some point I see that I cannot improve, and so I'm going to select the one that produces the best results, or the ones. Okay. This is well, in numerical methods, we are taught to do that, no? When does the model converge, the numerical method? Well, when there is a threshold of error that tells us that we can consider that we converged. Well, the same, but retrying the conditions of our experiments. Example. Consider that I collect data. I imagine an IoT, Internet of Things setting in a house. So I deploy sensors in my house in order to observe electric consumption, indoor temperature, humidity, gas consumption, outdoor temperature, outdoor humidity. So all these data are collected. And I also consider meteorological values that can affect the conditions of my house too, okay? And using all these observations, I would like to determine whether does it make sense to invest in low carbon technologies to modify my house and or not, okay? Now, of course, you can see that this data have a high level of variety. They are quite heterogeneous. Some of them can be produced continuously, others not. And then, well, the idea is to use them in order to predict this, answer this prediction question. So my experiment will look like this. I will go back to the general representation. So first of all, I will have a lot of data. The first thing that I have to do is an exploratory procedure, set of operations that will help me understand the content of the data that has been collected, and then try, for example, to produce an integrated data set or determine the conditions in which my data arrive to the experiment. For example, seeing whether there are outliers, null values, etc. All the aspects that we are taught in statistics. Okay, so this phase is called data preparation. Okay, so the objective is, at the end of the day, to determine whether the set, the conditions in which the set of data arrive to me, and then the quality of these data collections. And the main question is whether this data collection can contribute to answer my question. Okay. So that's the very first part. Quality of the data, degree of veracity, and whether the data are enough, give enough evidence to answer my research question. Okay, and then the derived question is it possible to drive some data engineering modifications of the data, preparation of the data, such that even if in its raw condition cannot contribute to answer my question, by preparing it, I can produce a data collection that can really contribute to answer my question. Okay. So this is the very first part of an experiment. Now, the second part is, once, let's assume that the collections that I have can be prepared and integrated in a data collection that can be used to answer my question. The second aspect to consider is what are the different processing steps that I'm going to perform to this data collection in order to answer my question. For example, in the case for determining low carbon technologies, there are two things that I need to know. First of all, the energy consumption profile of the house, because with this energy consumption profile, I can determine the CO2 footprint of my house and then evaluate it with respect to determine whether I'm low carbon or not, and whether I need to improve the my CO2 footprint, so reduce it. Now, how do I know this? Because I have to interact with experts. Okay. Another aspect of data science is that you can never decide, if you are not the expert, you can never decide on your own which are the steps to be addressed in order to answer a question. So an energy expert will tell you, well, if you want to determine the CO2 footprint, then you first have to have a profile of the energy consumption, and normally energy consumption is determined by in-house observations and also by out of the house observations, so environmental observations like the temperature, the seasons, etc. And so all these you need to integrate such that you have a good energy consumption pattern, and then with this, depending on the location, etc., you can estimate your CO2 footprint. So once the expert tells you this, then you perform design the different steps, okay? Why do I have here several boxes? Because you can have different strategies in order to model the energy consumption, in this case of a house, okay? So every possibility that you can identify that is potentially interesting for answering your question, you are going to consider. Okay? And then once you have this, you can complete the answer and not only understand, have the footprint, but with the footprint and the behavior of the house, you can eventually predict whether the energy consumption and CO2 footprint will be reduced if some conditions are verified. So the idea is to see whether if I reduce these two elements, I will reduce my invoice. And if I reduce my invoice in a significant manner, then maybe it would be interesting to have low carbon technologies. But all this that I'm saying does not concern the experiment. The experiment is just giving me elements, arguments, to then reason about the question and then provide some possible answers with respect to these arguments. And this is, in that sense, I say that the result is not definite and it's in general incomplete. Okay, you will never have the answer, yes, invest in low carbon technology. You will say, according to your the estimation, your energy consumption and your footprint, and considering the cost of your invoice and the cost of the materials, if you reduce, then you can eventually have, it can be interesting for you to invest in low carbon technologies, okay? But all the rest is, of course, with the help of the context and of the expertise of somebody else. Well, this is not done in one shot. It's not an SQL query that you write or a Mongo query that you write and it is there. In fact, it needs a lot of loops where you test, you have some results, you try something else, you have your results, you compare, you interact with the expert, you come back, you calibrate, and at some point when things seem to be acceptable for the person that is asking, so an expert, and yourself with respect to the scores that you have, then you proceed to the next step and to the next and to the next, until out of this recurrent process of design, you will have a stable experiment or set of experiments that you decide that can be used in real conditions in order to answer questions like this for any type, for any use. So this brings me back to here. In fact, there is a general schema of a data science pipeline that consists of the following elements. First of all, as I said, you will perform a data exploration and preparation set of tasks that include having a quantitative profiling of the data. Here is all about distributions, all about null values, all about outliers, okay, things that we are used to deal with in engineering. Then the second set of steps is, once I have the profile, is it possible to perform operations that can clean the data, that can improve the data set? okay? For example, if I have outliers, is it reasonable or possible to impute my outliers? If I have null values, is it reasonable and possible to impute the observations that have null values, or using the other data, can I extrapolate, for example, the missing values? Okay. Can I work with my data distribution, the distribution of the data, such that I have a more well-distributed, normalized, for example, distribution of my data, or a more balanced observations with respect to a given variable? Okay, so this is data engineering, for example. Do all the variables that contained in my observation are necessary to answer the question? This is variables reduction that we also study in engineering, particularly when we study statistics. Okay, so we use these tools that we already know in order to determine the strategy to adopt to deal with the data. And note that here, I'm not addressing the question. I'm just playing with the data, exploring. And then, do I need all the data to answer my question? Or can I select a representative sample of observations in order to then proceed to analyze them and answer the question? Okay, and sample selection is also a knowledge that we have from statistics, right? And of course, we can rely on visualization techniques in order to help us if we have the luck of being visually able, in order to understand the different quantitative observations and modifications that we perform on top of the data. Okay. And once we have performed this, the resulting data, cleaned data set, will help us decide whether we can proceed with the set of tasks that will contribute to answer the research question. Okay. The first thing that we have to determine is whether the question is seeking for hindsight, insight, or foresight. Okay. What type of question I am trying to answer. And then, according to this decision, then I can identify potential algorithms that can be applied in order to answer it. And depending on the different algorithms, I will still have to do some fragmentation, for example, of the data. If we use regression, I will have a set of data for which I'm going to train the model, and then another set of data that I will use to test the model, right? That's something we do in regression. I rely on regression because I mean, that's something that we learn in engineering disciplines. But this can happen in other using other algorithms. No, so if I need to fragment, then which are the best ways and strategies in order to fragment my data, such that the model will be trained and then will not be biased, overfitting, or something else, right? The more I decide of the tool, of the algorithm that I can use in order to analyze the data, then I must validate the results. I must insert in this process an assessment process where I compute the error margin, I analyze the error, and then I can perform an adaptive analysis with the scores and then determine whether I am obtaining good results or not. And then the question is, if I'm not obtaining good results, or if I'm obtaining good results, why is it? Because excellent job, and I really calibrated correctly my models, or is it by I simplified a lot, and then of course I'm using good results, but when I test them, the results are not as good as expected. And the same with error. Does it come from the my strategies, my cleaning, or my fragmentation or training strategies, or the poor solutions come from the fact that I didn't choose the right model to analyze the data? And this is all the complexity of the decision making and the design of the experiment. If you see, I mean, it's a very dull schema. So you have two general set of activities, and then visualization and assessment. Here you can even have visualization, but in itself, it's not a complex thing to consider. The problem is that inside all the decisions that you make, there you have a complexity, and this makes it very laborious to design and to perform. Okay, and this is why data scientists today are required in the market, and salaries are normally good, because this is very laborious to do. Okay. And then if I go to the limits of my example, as you can see here, for every, so here in my data preparation set of activities, I perform different strategies in order to explore. I can also use different analytics methods to profile the energy consumption and then estimate the CO2. And then eventually I can have some results, and that can lead to a conclusion. For example, it's a good investment. I mean, if you invest, what you will gain is reduce CO2 in Christmas and summer. That's the only thing that you will gain if you invest in reducing CO2 footprint, for example. No. So questions until here? Let me see if I have questions on the chat. So, and how do I do this? Here is the chat. No questions in the chat. Okay. So if you don't have questions, let's continue a little bit. We are very close now to having a little bit of a hands-on, so that you can wake up and have a concrete experience on a first. So this was the workflow, but then the data science workflow in itself, it has a life cycle, okay? And this is important to consider, because this concerns the maintenance of your experiment. Of course, okay, you will invest time and a lot of effort, etc. And at some point you have your experiment, it works well, it serves to answer questions, etc., to make decisions. But then it should be, it has a life, okay? It should be maintained, it should be observed, etc. And so we need to have a look at how does this life cycle works. Well, for the design, in fact, you can have, of course, an understanding or an observation of a problem. Then you can collect the data, you can explore them. So this is the exploration part. Then you have to eventually, as I said, clean and transform. and then go here in a loop. And once you are ready to go out of the loop, you can produce a model, then you validate. And if you're happy, you continue. But if you are not happy, then again on the loop. And then eventually you converge for a moment, and then you deploy your solution. In every step of these different steps, you need, if you want to manage the life cycle of this pipeline, you need to collect data in order to keep track of the conditions in which you perform these activities and in which you make the decision whether to consider to move forward or to move back. That's the design process. And once you have deployed your solution, in fact, normally the experiments work well for a time. But then new data start coming again, more and more. And in many cases, the performance of the experiment starts to decrease. And you have to be able to observe this such that you can go back through a design process, a maintenance process of your experiment, and then come back to good performance scores, okay? And this decision-making concerns the life cycle of the pipeline. That's first thing. Second thing, the more you loop and the more it takes human effort to be defined and also computing effort to be defined, you increase the cost, economic cost of your experiment. So you also need to track how many loops and how much resources you use, computing resources you use in calibrating on this, because this allows you to determine the cost of the experiment, not the price, but the cost. Okay, how much did it cost in computing resources, in human power, to achieve this, to have this experiment? And then how much did it cost to maintain it, to observe it, and then to maintain it? Okay? This is why the life cycle is important. But you, as if you are from other disciplines, not IT disciplines, the only thing that you have to be aware is about the life cycle, about the fact that this pipeline is observed, and an IT team will deal with these problems and will tell you, you know, your experiment is not working very well. So you need to start over again in some phases so that it can have good precision again. Sorry, I'm very sorry, but I started at 3 in the morning. So at some point, the body reacts.
No problem.
Thank you. Okay, so this is the life cycle. But as I said, it's just to make sure that you have this in mind. But as well, this is for an IT team to be managed. But here is what you need to be aware of. You have to decide as engineering experts, what is the conditions of your data, and when are you going to go from factual querying towards other types of query. Okay, this is very important. Okay, and a help to have in order to guide your observations and your decisions is the rawness degree of your data. Okay, the more raw your data is, the more you will need to have experimental approaches and not be able to perform factual approaches. Okay. In fact, well, this is a historical pedagogic way to proceed. Normally, we all start learning this point of the spectrum, where data are very curated. The design of the database has a very constrained process, so your data is really in the best mathematical conditions possible, and we learn to perform factual queries. But in fact, this is only possible once our data have been transformed from very raw data into very curated data. Okay. When we go, so here, so let's start from what you know. Very curated data is data that lie, for example, in relational models. Even the data, even if it's a little bit dirty, the data that you have in Mongo are very curated data, okay? Other examples of data, of curated data, is the one managed by search engines. The representation of data in search engines is a mathematical one. In fact, they process the terms, and they have a statistical representation of the terms, the frequency of the terms in a text. That's the representation that uses the search engine in order to help us find sites, pages. So this is a really curated representation, and then on top of it, we can express keyword queries, for example, in information retrieval, and or relational or Mongo-like, which are look like relational queries, but they are anyway factual on top of this. Okay. But now, when we are in the other side of the story, and we have very raw data, querying objective in huge, and I mean in very raw data, is in fact data exploration. Nobody can use data that is very raw. Okay, dirty data are not good thing to do, to use. And so we need to explore them to understand why are they to which extent their dirtiness can impact the further analysis, and whether they have a hope, whether we can clean them. Okay, so that's what we have when at this level of rawness. Okay, once we start moving into less rawness and more curation, then we can start progressing and being able to answer hindsight queries, insight queries, and foresight queries. Foresight queries, for example, need a lot of clean knowledge. Okay? For example, if I want to predict whether the price of I don't know, of energy will increase, I will have observations, for example, economical observations that determine the price of energy, and I will say, under these conditions, energy increased. Under these conditions of some percentage, under these conditions, it decreased, etc. And this knowledge can be then used to predict. But I need to have a lot of knowledge of a phenomenon and of an object study in order to expect to have good prediction or the possibility to predict. Okay? If I don't have this, I have to stay in this setting, either understanding what things are happening, or why did it happen, why did they happen, but never go to this, because I don't have enough knowledge to have more ambitious expectations. Okay. And then, of course, on each, you will have tools. But the tools are more or less, I would say that the tools, the fact of using some regression or some model, are a cherry of the cake. Okay. First, the real problem is determining where we are. And once we know where we are, then we can have a look at the models and the tools. Now, this resumes everything that I have said in almost an hour. What time is it? Yes, more or less an hour. Here you have classic querying strategies. So for Eric, I think that was the one who was not sure about the difference between classic queries, factual queries, and the experimental queries. Here you have the clean answer, okay? So when we talk about these queries, these factual queries, we are talking either about relational queries. I want to correlate data. I want to correlate employees with departments, for example. Okay? They can be multidimensional. They can be spatiotemporal. They can address aggregations, max, mean, average, etc. They can look for patterns, or they can look for regular patterns, regular expressions, okay? Then in other settings, like in information retrieval, the queries are conjunctive or disjunctive. So this is what we use in Google. Key terms, and we can combine them with and ors, okay? And sometimes with negations. Or they can be navigational, okay? For example, if you have a graph, you can search for the path, given one node, search for the path that will lead you to another node, for example. So these are navigational queries. Well, in Mongo, you have navigational queries and you have regular expressions. Then the execution model of the query here is on demand. So until I explicitly ask the question, then I will have an answer. If I don't ask any question, I don't have an answer. But there are also other techniques that allow us to make continuous queries. Well, you are young. I don't know if you have seen or used RSS on the web. So you can subscribe and receive notifications if a web page has changed. And these RSS notifications are continuous queries. In fact, you say, I want to be notified about modifications. So the query recurrently is observing a site, and when there has been a modification, then you have your answer, which that says that the page that you're interested in has been modified, has new content, for example. So this is continuous queries. Now, normally, since we consider that we have all the evidence in the database, the completeness is full. And in some settings, for example, on information retrieval, it can be partial, okay? Or it can be fuzzy. In the case of information retrieval, this is approximations. Remember that when we perform a query on a research engine, there is precision and recall. So this, to which extent the result answers my query, and to which extent the answers that really correspond to the query are precise. You have to do an answer for this query. And there are other probabilistic strategies. So you see, even when we start moving from very mathematical properties associated to the data model towards mathematical representations, but with less strict mathematical properties, we start having this notion of approximation on the results. And then the representations in very mathematical classic databases are intentional, and in others are extensions. So we have all the, in the web, we have all the pages. And now we are moving to data science queries where they are exploratory, okay? Remember that the workflow is there once you worked a lot with your experts, your colleagues, etc. And at some point you have the final experiment, but this requires exploration in the sense of by construction, okay? Step by step, as it's said here. Then the objectives are modeling or prediction. The execution is even done step by step. So you can have the partial results of the experiment. They are approximative and they work with extension because they work with the data and in some conditions with raw data. Now you will see in the remaining set of sessions that we will have today and in the next in 2 weeks, is that it is possible today to write experiments in a more or less comfortable manner, meaning comfortable that the degree of implementation of the experiments is not very high. Because there is a democratization, both in data collections and in algorithms. So there are a lot of libraries you've seen in R, and since you come from engineering disciplines, maybe you have used MATLAB, and there you have, in both cases, you have, I mean, all the functions and all the algorithms possible, right? Only if you have a very, very concrete problem, then you would need to implement, but otherwise you have the tools there, okay? And so the only thing to just to consider as users is that you have to think about the quality, okay? And the way these both algorithms and data collections arrive to you. Okay, particularly with algorithms, there are X number of ways of implementing all the models possible. So it's important that you are acquainted with these hypotheses made to implement them, because they have an impact in your results. But anyway, this allows to make life simple, and in fact, focus on the real challenge, which is designing the experiment. Now, this means anyway that we will be combining mathematics and statistics. So this is good news because you can rely on your previous knowledge doing data science. Well, we need anyway some computing knowledge. You will see that at least, well, in R you have already seen, but you will see that in the kind of tools that I'm going to introduce, it's really very simple. And then this part we will not touch, but it's important that you bear in mind that business is there and that value is there, and that eventually, once you develop a solution, you have to interact with a business team in order to evaluate the cost of your solution and also the price if you are selling the solution to some company that you have to associate to it. And then other things like software development and traditional research, but software development at the first design moments of the experiment, you are not going to produce a software. You are going to produce a pipeline that will be then wrapped into software and become an application. But this is not for you. Okay, this is for an IT team, and what you have to, where you have to be really involved in the design of the experiment. This is just, I think that with Professor Joly, he had a more graph-oriented figure. This is just to tell you, I'm sure that he has already told you this, that in order to perform the smart analytics in general, we need to have a very good culture on the different tools that we can use. Okay, so he gave this graph representation. Here I have a tabular representation. So what is important, and that you will see because there will be several sessions regarding, for example, regression, but you have to really master the knowledge that we acquire in engineering, in fact. So Bayesian networks in from statistics, Markov chains, regression models, regularization, all these families of models come from our engineering education. Okay, so they have nothing to do with artificial intelligence or something else. The dimensionality reduction is also something that we learn how to do in engineering, and again, it doesn't have anything to do with artificial intelligence or other models. Okay, so important is to have a very good culture in the mathematical basis that we have because of our engineering education. Okay, make sure that they are here. Okay, and then since we are we would like to test other things, and because they can be complementary to these mathematical models, it is important that we are acquainted, for example, with clustering. Clustering is a very useful technique, and so be aware of the principles of clustering and algorithms that implement clustering techniques, decision trees. The rules maybe, I would say that they are less important, even if they are interesting. So I would say this, the neural networks and deep learning, particularly because they are becoming popular, okay? And it is important to really have an expert in your domain's position with respect to the benefits that they have for the type of questions that you have to answer. Something important to consider is that these methods, the promise is that they can have very good results, modeling and predicting results. The problem is that they require a lot of computing resources. And since we have value in mind, this means a lot of money. Okay, so in the last weeks, there is always every 5 years, the artificial intelligence community produces a manifesto and a report of the discipline. And in the last one that appeared some weeks ago, one observation is that today, the models that are really used in day-by-day solutions are trained by companies because they require billions of dollars to be trained correctly. Okay, so it is important to bear this in mind, because if you are in a company and you decide to train specific models to solve your solutions, you must be aware that you have to balance with respect to the expected return of investment that you will have by solving the problems, okay? Otherwise, the cost will be high. If you use your own servers, and if you use, even if you use the cloud, a cloud subscription in industrial settings is very expensive. And if you add the fact that you need a lot of resources, it will really have an economic impact in your value. So it is important that you make the clever decision when you decide to use this. Okay? In the master, it's good to use them because you can get acquainted with them and you can see the principle, etc. But then in real conditions, there are other decisions to be made. Well, oh yes. once it doesn't want to move, and then the next, it moves very quick. So as you can see, it's having problems. I don't know why. Okay. I wanted to show something else, and then it's just moving as it wants. Okay, 2 slides, and then what time is it? Yes, 2 slides, and then we will start moving. I think that we are going to really have a little bit of hands-on today. Now, something to know about data science pipelines is that today they are done in an the design is artisanal. I don't know why it's not showing, but I continue speaking, you can see it there. And normally the solutions, you need different tools, and these tools are done by hand and by IT people, okay, with a lot of technical effort in order to integrate different tools. So you will, you are already having the experience, right? Because you are connecting Mongo to R. Okay, and so you have to learn how to connect it, the details on how to connect, to contact the server, etc. And this is just a very simple example. Then once you retrieve the data from sorry, from Mongo to your notebook, then there are other things to consider, particularly how much interaction you will have in order to get the data that you need to use, for example, in R. So this kind of technical details are increased in real conditions, okay? And so it's important to consider this. And then, I hate when it doesn't work because, okay. And so the challenges are that we need to have anyway tools that allow us to ease our lives. Okay? In terms of the preparation of the execution environment, and then also in terms of, we have seen that the experiment design is a loop. And so that the loops that you have to perform only concern your design and do not concern also technical aspects that you have to calibrate besides the experiment design in itself. And you will see I think that we will see this today, there are different tools that allow us to ease our lives and do these complex things as transparent as possible. Okay. So this is your general culture. So I will use some more minutes, and then I will proceed in the same way as before. We will have like 10 minutes break, and then we will continue. And for those that arrived a little bit late, we will finish at 12. And this is why we are having this tiny coffee breaks. Okay. So let's move to the toolboxes. As I said at the beginning of this sessions, is that the message that I want to pass is toolboxes, okay? What are the environments that you can use beyond the fact that you can install R in your computers? In fact, what you have to know is that there are 3 families of environments that allow you to execute experiments. In the middle, you have RStudio-like solutions, okay, where you have a set of libraries, a programming language, an description and execution environment, for example, a notebook, and then you rely on either on your computer or in some other computer in order to execute, to run, for example, your notebooks, okay? this can be done on your computer, but also on other types of architectures that can lie on the organization you work in, for example, in the school. And or they can go be really externalized, run in external servers where you do not have longer to either install nor go and have a look for libraries if you have missing libraries. Everything is managed in an external solution, and the only thing that you need is a browser and connection so that you can have your notebook environment, and then the rest is execution and resources are provided externally. Okay, so this is the spectrum that you have in this a type of environments. In a minute we will see why they are called why. Okay, so now there are this is good when you are addressing in-house design of your experiment. Even if you need a lot of resources, I mean, you are working in not real conditions. Deploying a solution implies changing the scale, okay? So when you start moving to other scales, there are other families of technical solutions that provide tools that can address other tools, different tools, and also run in more ambitious architectures. To the left, this is these are platforms that emerged when the peak of the big data trend was up. And so they are called platforms and stacks because they are made out of layers. And in each layer, you have plenty of solutions. With particularly with Professor Bobino, you have, I mean, the message is that storage is important and you have to have the right tool to store your data. And then, of course, to retrieve your data through querying or other things, okay? So this is here. You need storage, so you need disk. And when we are talking about large scale conditions, then you need farms of disks because we are talking about volume, okay? And there are tools that provide you with access to this type of disks, farms of disks, or that can help you manage a farm of disks that you can have in your organization. Okay. Then there are other tools that on top of this give you access to the data that you store in these farms. We ourselves, for example, are users of this kind of solutions. If you are Dropbox or Google Drive or OneDrive users, particularly in Dropbox, it is very evident. It is in fact a storage solution. So they have, as a company, farms of disks, and you buy space. And the space, you don't know exactly if it's one disk or several disks. You know that you have access to distributed space that you see in an integrated manner. Then you store, so you use the space of the hardware of disk. And then they provide you with a file system that gives you the illusion that you are managing the files in a centralized manner, but in fact it is distributed. And then they even provide you with an application that runs on the web or on your machine that helps you manage this storage space. And eventually, if you require more space, then you can buy it. Okay? And they promise accessibility. So this is this. Then there are other tools that regard, once you have this distributed solution, then you can need processing solutions, and horizontal processing solutions, okay? So you can have them here. Then here you are acquainted already. At some point there was a Mongo somewhere here, but I think that in Christoph's sessions he also talked about Cassandra or other NoSQL solutions, and here you have Oracle. So you have all the data management solutions, and they all rely on this. Okay, it's a stack. Then you can have other tools in order to manage your resources and then software. Okay, so these stacks, how are they delivered? In virtualization solutions. So the companies provide virtual machines with pieces of all these stack of these levels in one solution that you can install on your computer, on a cluster, or on the cloud. Okay. So this is the way they are delivered. And then many vendors, and particularly when machine learning and artificial intelligence started to acquire again a lot of importance, they started to provide what they call machine learning services. In fact, they connect to at least 3 elements. A high-level interface where someone can design in very friendly manners experiments. Then the libraries necessary to really analyze that can be heterogeneous. Here R is represented, but you can combine R with C implementation, with Python, with anything, okay? And so they provide transparency layers that allow you to work with any tool in a transparent manner. And then all the parallel execution that is required when you change scale, okay? And all this is given in one integrated solution, and so people can develop their experiments in a very comfortable manner, and then decide whether they access them locally. Look, when I say locally, it's not your computer in here, okay? Well, we will see that it's possible to have tests on your computer, but normally is, I mean, in some large-scale environment, and then particularly you can use this on the cloud where you can have a lot of resources available. Okay, so these are the 3 families. As I said, for first design of experiments, we are here. And you will see that even here, we can have a lot of resources. Questions?
Mm-hmm.
So before we go for a coffee, an important thing to consider that you will experiment directly in the project and in the course is this. In fact, the analytics world lives its life, and the storage solutions live their life. And there is a divide among both of them, between both, okay? So this divide is not to you to, I mean, it's to you to identify, but it's not for you to solve. Okay, the divide should be solved again by an IT team, not by you. But it's important that you see it, and this is why we decided when we designed this course to have this, for example, Mongo experience, then have R as analytics environment, and then show you that it is possible to connect. But then once you connect them and you retrieve the data, you have to decide to which extent you rely on Mongo to do your certain activities, or once you get the data, then you stay here and never again interact here, okay? But, well, this is formally expressed as a divide, and the divide concerns data loading. So now the exercise where you connect R with Mongo and you get the data is this, okay? And why is it a divide? Because you have explicitly to tell your notebook on R to extract data, to connect to Mongo, and then extract the data that lies here, there, okay? But there is no continuous interaction between both environments. So this means that let's think that you have a lot of data in Mongo and you do not have enough main memory in your computers. You will have an error, or you will just retrieve part of the data, even if it's incomplete or whatever, but there is no solution that can allow you to play with your cache so that you can still deal with a lot of data without having to perform some technical operation, okay? So going from memory to cache to disk is not automatic. You would have to implement something. Then data persistence, well, we will see in the solutions that I will show you that you can adjust and calibrate and tune some solutions, but otherwise in R, when you have you start working, right? So you have your partial results. Either you explicitly say that these results must go to your file system or to a store, or you lose them, okay? And then you have to re-execute the notebook again. And this is because there is no automatic persistence guaranteed in the results you obtain while executing the notebook, unless you explicitly say that they should go to and be stored, okay? Then query optimization. So once you have the data from Mongo, then all the guarantees provided by Mongo, and even including query optimization, you lose them. Now you have the data on the notebook, and it's up to you to manage this, okay? Then concurrent access, of course, it is not guaranteed, okay? So if you and your friend are interacting with the same notebook, in a, for example, in Colab, this is possible, in Google, then, I mean, and if you modify and the other person does a stupid thing, then, sorry, but no solution is done, is provided, okay? And then consistency control and access control, they are also not solved. And so this divide, this doesn't mean that this is not done. This just means that your IT group, when you are working in industrial settings, invests time in providing you with solutions for this. And in a company, if people invest time, this is human resources, and this is time to market, okay? So the time to market of your experiments is increased by the fact that someone needs to help you to address these problems. And then, of course, value again. Okay, so let me see, what time is it? Yes, we are going to have a 10 minutes break, and then we continue with storage, and hopefully we play a little. So see you in 10 minutes.
Okay.
So these data lab services, in fact, are a little stack of tools that allow us, of course, to store, but also to manage the data collections in a very detailed manner, okay? So if we have a look in general at the stack of a data lab service, it will have at the very bottom, of course, there is disk, okay? And you can decide whether you will have your own machine disk, a storage solution if you are in your company or in the school, at the school, or a storage solution provided by a cloud, okay, a cloud provider. example, Google Drive or Dropbox, or the one you prefer. Any of them, this is something that you even studied when you went into these file systems, distributed file systems with Hadoop. There is always a file system, okay? We never interact directly with the disk. Computing science has evolved enough to have this file system support that allow us organize the data, etc. on top of it. So they provide, this is the very basis of a data store solution, okay? Remember that any data storage solution, including relational solutions, including non-SQL solutions, at the very bottom of the internal engine, they deal with the file system, okay? So very basic storage solutions. And then you have two types of other services in the next layer. You have storage solutions. I remember that Christoph showed you a kind of layer-based figure where you had the storage with the specific operations that you could do, and then while you went up in the stack, there were the NoSQL systems with more querying possibilities. Okay, so this is more or less the materialization of that reference stack. So on top of, as I have said, on top of the file system distributed normally, you have these storage solutions that allow you to have more evolved interaction with your data, okay, through queries, for example, or through analysis if you are using Hadoop. And you can also have program-oriented solutions, like using Python or using R in order to deal with your data, okay? You have explore your data, okay, from a programming perspective. So either you use more or less declarative solutions or you use programming solutions, but in any case, they interact with the file system and the file system with a distributed storage support at the bottom. That's it. And then there is the last layer. In fact, the idea of a data lab is not only to store and to query the data and explore the data, but it's also there is also an objective of curating the data. And what does it mean to curate the data? It means to provide enough descriptions such that the someone that is not you, and if you decide to share the data collection, that is able to understand what is inside, okay? So a lot of metadata, the quantitative profile of your data, the frequency in which your data collection is updated, the size of the different versions, the context and conditions in which this data is collected, licenses in order to determine whether someone can access them and for what or not, descriptions of other experiments that have been performed on this data. So all this curation description is also maintained through these data lab services, okay? And there is also, the idea is that your data collections are alive, right? So they evolve in time and you can version them. And they provide with versioning solutions in order to manage the different releases of your data, okay? And all this in an integrated stack that can have a friendly interface or that can be more technical, but anyway, with all these services, okay? Now, many vendors, particularly vendors and companies, the big companies in computing science, have solutions like this, okay? So here I enumerated three. There's the Google solutions, Kaggle and Google Colab. And then there is one also from Microsoft, but there is also IBM and Amazon, etc. So the big companies have this kind of data labs, and the idea is, of course, to have to ease the life of those that are producing the data, but it's also the idea of the possibility of sharing the data collections with publicly or with certain communities, such that many experiments can be performed on top of them, or that experiments can be reproduced in order to validate the results that are claimed by someone. And what we are going to do now is we are going to have a look at an example. We are going to start with Kaggle because it has many interesting functions, and it's also very popular in data science. And in the other sessions, we will play with Colab. Okay. Now, for Kaggle, we are going to do the following. So I'm going to stop sharing. Yes. I'm going to go here. So again, first of all, Data Lab. We are going to do the following. Since the idea is to show you an externalized solution, we are going to use the cloud, okay? And we are going to use, in fact, two clouds. First of all the data that I have prepared together with my team for this course are lying on GitHub. For those that are not acquainted with GitHub, GitHub is a cloud service from Microsoft that allows to manage code versioning. Okay, but after now that data science has become very popular, many people share both the data that they use for designing experiments and sometimes even experiments. Okay. So if well, you have it here, and we will use different services of GitHub, particularly storage, file system, of course, in order to deal with the data. So we will, in fact, we have used them, and I'm going to show you how to connect to this storage environment and use them in your own Kaggle environment. And then the second cloud provider that we will use is Google. And Google will provide us with very interesting things. First of all, it will provide us with different kinds of computing chips, okay, with different processing capacities. It provides us with storage space and with tools that allow us to store and go explore the data that we have. It can be code and data, and then other compiling environments. Here, Python is represented, but there is also R. And then it also provides, as the one that we are going to use, software interfaces and applications that can be can allow us to have friendly interfaces in order to deal with both our data and eventually our experiments. And the interesting thing is that we only need the browser in order to use them. Because, in fact, just to be sure that we are all on the same page, in fact, we are using, well, they are providing a cloud solution. You must remember that the cloud is an architecture. Okay, and the architecture consists of reference architecture that has 3 levels. Okay, the architecture is a layered one with 3 main layers. And all the layers are organized. The unit of organization and of access to the cloud is called a service. Okay, A service is nothing more than a hardware of or a software element entity grabbed and hidden behind an application programming interface. Okay, it has methods that we can call. Okay, that's a service, and the service can be deployed in a computer, in a server, in whatever, or in a data center managed by the cloud. Okay, and so across these layers we can different types of services. We can have infrastructure services, and the layer is called infrastructure as a service. So here I enumerated the most popular ones: CPU, RAM, and disk. But this, you can have many different technologies of disks, RAM the same, and also CPUs. I mean, CPUs are not the only ones. You can have other processing chips that can be used in order to process our data. So you can have tensors, you can have GPUs, different types of hardware that are accessible as infrastructure as a service. Then you have in the next layer platform as a service with, for example, compilers, with example, libraries. Mongo, for example, could be a platform as a service. So this kind of horizontal tools that we use in order to program. And then at the very top, we can also have software as a service solutions that allow us to access to applications that are also deployed and running on the cloud. So those that use Dropbox, it's a very useful thing to be used as example. So for example, for Dropbox, it gives us access to many disks deployed in a distributed manner. It provides us with a file system that when if you see in the browser, we have this file system where we define our folders and we organize our files, etc. This is a platform as a service. And it also provides an application that can be accessible on the web, or we can install explicitly Dropbox application, and then we can deal with our files and also manage the amount of storage that we want to subscribe to through the application that can lie on our computers or we access on the browser, okay, or from our telephones or whatever. And so this is a vertical cut of a storage solution through these three different cloud layers. And the particular thing about the cloud is that it provides ready-to-use environments. And the also particular thing is that all these services are provided under a pay-as-you-go economic model, which means that we subscribe to a cloud provider, and the company provides us with certain amounts of different services, okay? And it is elastic, and it provides the illusion of unlimited access to resources, because if we need more, or we reduce the number of resources that we are subscribed to, it is possible, modulo the fact that we need our credit card to subscribe, right? So this is what I have in mind when I explain that we are using different levels of services on the cloud. And another interesting thing is that everything can be externalized, and we just need our smart telephone to come to the class and do analytics. So if we go back here, for example, in Azure, which is the cloud of Microsoft that provides the solution, then we have storage. So infrastructure as a service. We have the file system and the versioning system, which are platform as a service. And then it is possible to have an application on the web, which is software as a service, okay? In the context of Google, we have also storage, disk. We have different, and also different types of processing units available. And this is infrastructure as a service. We have platform as a service through the file system and through the interpreters or compilers that we use, for example, for running notebooks. And then we have also applications accessible. This one is on the web that look fancy and that help make our life easier to access all this. Okay, they hide all this complexity behind a web application. Okay, so this is back on the scenes, and now in the minutes that we have left, so half an hour of session, we are going to have a look at Kaggle. Now I'm going to stop sharing and then share again because I need to share my whole desktop. And this is the desktop. And another thing that I'm going to ask you is the following. On the chat, I am going to write the address of Kaggle. I will kindly ask you to subscribe to Kaggle while I explain the invite. I mean, I describe the invite and then explain what we are going to do. So you will need this, and then just give me a second that you need also this. Since casein is not on now, I'm going to give you this address. So do not worry, everything, all the links will be in casein just after this session. So, I'm just going to write this address on the chat so that we can work together easy. So the idea is that you do as I do, okay? And this will prepare for the analytic sessions that we will have in 2 weeks. So just make sure that you follow and you cry out if you feel that I'm on a highway and I'm not waiting for it. Okay, so I'm going myself to go to Kaggle. And close the chat. So the only thing that you have to do is go to Kaggle and you create an account. Okay, so I did more manipulations because I haven't opened Kaggle before. Okay, so once you subscribe, you will land to an interface that looks as my browser. In the left-hand side of the app, it has many services. We are going to use data sets, which corresponds to the data lab. It's an implementation of the data lab that I have described some minutes ago. And then the next sessions, we will play with this one, which is the experimentation environment, okay? So, but today it's data sets. So I'm going to click to data sets, and if I click to data sets, I arrive here. This is the interface of the data lab, and you can see the following. You can see that there are many data sets shared by the community, okay? The data sets, let's choose one, this one. A very glorious data set, anyway. So when you click on the data set, you have a title that is representative of the data set. You can have a description, a textual description of your data set. And then many metadata that are either automatically computed by the system, by the data lab, or explicitly given by the owner of the data set. For example, the usability is computed by the system according to an analysis that it makes both on the descriptions of the metadata and the data itself, okay? And so here, this is a very nice one because it says, you see, it is complete, it is edible, it is there's compatibility, etc. So this is a first step to the evaluation of veracity of the data, okay? So it analyzes and then provides a score according to some references that are explicitly given by the system. And with respect to this, it gives a score, and you, when you want to use the data set or when you manage your own data set, you will seek to improve, if you want, the this usability score. Okay. Then it allows you also to license your data and have other descriptions. For example, here it is a one version data set, so there is no updates. But if the data set is frequently updated, it tells you in which frequency the data is updated. And then you can also add tags in order to have a representative observation, representation and description of your data. It also has, well, it works as reputation. So if others use your data set and they want to score it, they can. Okay, both when using it for an application, for research, or for learning. Okay. And then at the very bottom, what we can see is that when you upload a data set in a format known by Kaggle, it in fact processes it and provides the quantitative profile of its content. Okay. So for example, here, it says that the data set is contained in a CSV format, a tabular format, or in a file called this. It is version 1, and the data set is around 5K kilobytes. And then you have in the right side a summarized description, quantitative description of the data. So again, I have one CSV file, and here I know that the CSV file has 23 columns. 10 of them are of type string, 10 of them are decimal, and 3 of them are integer. Okay, so you have the structural description of your data collection. Here, well, the owner provided with some description of the file. And then the system also computes the famous quantitative profile. What does it contain? For every column of the data set, it computes the distribution of the values that is even plotted. And so you have rank by wealth, and you have 2.5K different values with this distribution. And again, when the values are decimal or integer. For columns that are string, it gives you all the number of different terms used in the content. Then it also gives you the unique values. and this for every column of the, you see, for example, here it has also the quartiles of the content, okay, for the string elements. So this is a detailed observation of the data set. Then you can have a compact observation where it provides you with the content, and then a columnar representation. So for every column, you have the distribution, as you can see, it's interactive. You can have the number, the percentage of valid values, mismatch values, missing values, the mean of the values contained here, the standard deviation, and the quantiles of the data. Okay, so for every column, for every 23 columns. Okay.
What does mean mismatched?
Mismatch is that they didn't correspond with among the different for the same, for example, for men, for the same conditions, they correspond always to the same values. So you don't have two values associated to the same type of observation. So wonderful, you see, because in one shot, we have part of the exploration part done, at least the quantitative approach. Okay, then we have to engineer and see outliers, etc. But the very first quantitative profile, it's automatically processed by the system. And what is it I wanted to say? Yes, that's and then when you are users, you start creating your own data sets. You can decide whether they are public or private. And also, well, you have to take care as much as you want about the different descriptions of your data in order to make them usable or less usable to others and to you too. You can also imagine that if you start producing a lot of data sets and you do not have care of curating them a little bit, then you are lost in your own bunch of data sets. Okay, questions here?
It's quite impressive. There's no question.
Yes. Then we will see what ChatGPT does, which is also very impressive. But well, the idea is that you see that, I mean, for pedagogic reasons, it is important to know how to do this. Otherwise, you cannot evaluate whether this is reasonable or not. But then, when you are in more professional or industrial settings, it is important to be acquainted with these tools because these reduce time to market. And in industry, time to market is a very important thing. So you have to be acquainted of all the tools that can reduce this time to market. And you are supported by your university knowledge in order to be able also to evaluate the precision, the quality of the tools. Okay, that's also very important since we have profusion of tools because all the main companies are producing their own. So this is also a very important thing. You will be decision makers. So as decision makers, you will have to choose the technology that best fits to your requirements. So you have to have the general criterion to help you make those decisions. And so ease of use, capacity to perform things automatically, precision of the automatic tools, etc. So a set of criteria that allow you to make those decisions. Okay, so in the last section, so let's create our own data set, right? So I'm going to go back to to the data sets section. And as you can see, well, there are two main buttons. There is when you want to create a new data set, and you can maintain also your work. I'm going to click to my work, even if it's a little bit of a mess, but to show you that, well, here there's my profile, but then here I have many versions of the for the course with the data that I have been playing with. And so that you can keep track also of your own thing. And for example, for the course, they are private, but then, as I said, you can decide when to make them public or not. Okay. So, but now we are going to, well, you are going, and me too, to click to new data set. And so, remember that when I showed the stack, I said, either the data can come from your own local disk or from any other storage from someone, right? So you can have a link, you can have a file, so you can drag and drop or explore in your on your computer, or you can have links. So either the data can come from a remote URL, it can be imported from other storage solution, or well, there are storage solutions on the cloud like S3 or other the like. I mean, it's versions of NoSQL storage support, but particular to Google. Okay, that's there. Or they can come from GitHub. So we are going to choose GitHub because, as I showed in the back of the scenes architecture, we are getting the data from that we prepared on GitHub for the course. So you click on this. And I don't know why, maybe because I have few.
It's grayed out.
Wait a minute. No, I don't know why. Normally it should. Have a try yourself.
It's same. It's same. It's grayed out for me also. Continue. I cannot click on it.
Yeah, I don't know why. I have
Professor, we need to insert the link.
Yes, but oh yes, it's down. Yeah. Okay, thank you. So the link, I put it on the chat. And the chat, there is an HTTPS GitHub, and I'm not sure that you can copy it. So let me give you an alternative. I want to give you this address. You click on the address, and you are going to land here. Tell me if you do. So this is the description with they have changed the interface, right? But if you go to the link I have given, you will land here. And the only thing that I need you to do is copy this. Okay.
Sorry, I cannot get the link. So
just click on it, because since I am in an institutional Zoom, you cannot copy paste the link that I put in the chat. You can just click.
Okay, let me see.
The last one is http Vargas-Solar.com.
Yes. Okay.
You click on it, and then you will land to this site.
And then I copy the link.
No, don't copy.
Right.
Just click. You cannot copy.
Yes.
Oh,
But
well,
then
from
after
the
that,
side, yes. Then you copy the link, this HTTP GitHub. And then I'm going to close the chat. And then we'll put it here. And then we can continue.
Please enter
We have
GitHub.
to name our data set. So I'm going to
I'm lost.
sorry.
It's okay. I copied the link, but it seems to be not be valid GitHub URL. I don't know why. Maybe
Yes,
there's a
maybe you
slash.
added a space. So you are here,
Um,
and you're here.
yes, but this one,
And then
oh,
you
this
click
link,
on-
this is the right link?
yes, in fact, you go to the link I gave, and then when you land on the
Oh,
you copy the one that is a GitHub.
so I took the second one, sorry. So the second link. So it's the first one?
Because in order for you to copy, my problem is that you cannot copy from the chat to the to
I
here.
know.
Try
I
to
know,
copy
but there's two links in your in
the
the
second
chat.
link. If you click on the second link, you will
Yeah.
arrive here, and here you will find the GitHub address that you can copy.
Okay.
Right.
Which is the first link you gave in the
github.com. Yes, it's the first. Well, this is because I'm lazy and I want to copy paste. You can also write it. And so once you copy, you have this situation.
Yes. So then what I cannot
I give
do
you
is so enter. I need to enter a data set title. That's a
Then you click to continue. Now you are further than me. You are leaving me on the road.
oh sorry.
Now,
Okay, yes, I see your screen now. Yeah, okay.
okay, so now you give a title, the one that you want. I'm going to say Smart. I'm going to leave it private, but you can do what you want. And here you can see that for the time being, it says that there are files, but it cannot see the content of the files. This is because we organize the files into folders, etc., and it cannot process the whole tree. But once we will retrieve them, we will see them. Okay? The only thing that it knows is that this is the size, okay, 7 bytes. This is the size that I have consumed. And then you click to create. And you wait. And success. And you go to your text.
Just click to create after entering the name, right?
Yes.
And then
I'll
go to data
land,
set.
and then you go to data set and you land to your own data set.
Okay.
So for the time being, there is few things. We could add a description of the data. We could change this image to another one, write a subtitle. So start curating our own data with descriptions. So for example, it says, the current usability of our thing is 2.5, okay? And it suggests to add a subtitle, tags, and description to start increasing the usability, okay? For the time being, we do not update, so there's no frequency of update. Nobody has pronounced his or her opinion about our data set, so we don't have this, etc. But what is interesting to see is here. In fact, this, particularly this, when it's just you read Data Explorer, this is the file system. Okay, this is the service file system that I've shown you in my reference stack. And so you have the files, and now you can see that my files are ordered into folders that come from GitHub. You see here the little cat of GitHub. and each file folder has different files. Some of them are known, for example, CSV, others are of an unknown format. But as you can see, it tells you the size, how much does it weigh for every of them. And if I had added a README, it would allow us to see the README. But the README is empty. If you click, for example, on the first one, it creates now the quantitative analysis. And you can have the detail, the compact, and the column. Mine is poor as poor, not as the 4%. But the idea is that we click. This is why it's like this.
Okay.
So with this, we are ready next time to really get into concrete. We are going to use this data to start exploring. Have a kind of show of, you have seen now how to connect explicitly R to Mongo. You will see, I will show you an example on how to do it using ChatGPT by generating the code. So this is something that we are going to see. And then we will prepare 2 experiments that can allow us to do a lot of data preparation. This is useful because data preparation you have to do for the data that you have been given for the project, okay? You already have the Grenoble data, I believe, no? So it's on looking for outliers, looking for the distributions, and giving, the first result of data exploration and preparation will be the report, statistical report and plotting report on the conditions of your data set with respect to other hypotheses that you want to answer using this data set. So the first question is this data set useful in order to address my hypothesis? And so you provide the quantitative representation, the results of the data preparation, and you show how this new prepared data set can be used to answer the hypothesis. And then the next part, which will be done by Professor Joly, will be now that the data, supposing that the data has been prepared and that you know that it can be used, now show how to apply regression in order to answer some types of hypotheses.
So we need to know the question.
Yes. But in the project, you will have the question, right?
Okay.
Here, I will provide you with examples of questions. How do you, and then for the project, well, you have your own question that you have to answer.
Okay.
Okay, all is good?
Okay, fine.
Excellent. So let's go for lunch and me for breakfast. It is 7 here.
Oh, you're located in
Curitiba, in
Brazil.
Brazil. Yes.
Oh, okay. Oh, wow. Okay. I understand now how difficult it can be.
Yeah.
Okay, thank you a lot then.
Thank you very much. Pleasure to get acquainted with you.
Okay, see you next time then.
See you next time.
On 9th.
Have a nice day.
Thank you,
Have a nice day.
Professor.
Bye-bye.
Have a
Thank
nice
you,
day.
Professor.
Thank you.
Thank you. Bye.
Thank you.
Bye.
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 Bye. Nice.